Hello, here's another trio of nuclear physics, radioactivity, particle physics types questions. The following nuclear reaction occurs when a slow-moving neutron is absorbed by an isotope of uranium-235. So this is our induced nuclear fission. Explain how this reaction is able to produce energy. Right, so this is coming back to our binding energy again. So the binding energy of the products is greater than the binding energy of, well, in this case, the uranium-235. So, and the difference is released as energy. So it's always the way with these things. We're always looking at differences in binding energy. State in what form the energy is released in such a reaction. All right, so this is the kinetic energy of the products here. The neutrons will be going particularly fast because they've got low mass. So kinetic energy. Right, the binding energy per nucleon of each isotope in A is given. Right, okay, we've got those. Explain why the neutron does not appear in the table above. Right, well, there's no binding in it. It's just one, there's one nucleon. So it's not no binding between nucleons. There's just one nucleon there. There's just one of them, just one nucleon. So then we have to calculate the energy released, right? So we've already said here what's going on with the binding energy. So we need to get the binding energy of the products. So let's leave everything in MeV and we can just have that in our answer at the end. So the binding energy of the products is 141 nucleons in barium multiplied by the 8.3. Then we've got to add on the 92 nucleons in the krypton and multiply that by what is it, 8.7, and then we need to take off the 235 7.6s that we've got in the uranium. So if we type all of that in, and then we're going to get an answer which is in MeV, and it comes out 184.7. So yeah, nice little starter. Next one, a proton traveling at high velocity is fired at a stationary proton, stops momentarily at a distance of 2 times 10 to the minus 15 meters. So that's close enough that it might get in the range of the strong nuclear force. Calculate the electrostatic force acting on each proton when separated by that amount. So, right, our force, as we've done many times before, QQ over 4 pi epsilon 0 r squared. So we've got 2 protons, so we're just going to have the 1.6 squared times 10 to the minus 38. So we're squaring the elementary charge. And then we've got 4 pi times 8.85 times 10 to the minus, I want to say 12. Yes, 12. R squared is 4 times 10 to the minus 30. So we've got quite a lot battling away there. So let's get rid of those to make a 10 to the 4 on the top. And then we've just got to type in the other numbers. And then we'll see. Oh, actually, if I make that a 10 to the 2 and that a 256, I can then divide by these 4s twice to make that a 16. So we've got 16 divided by 8.85 times pi, and then multiplied by 100. So that's what we've got on all of those. So we're hoping on this, I mean, I'll stick it into the calculator and see what we end up getting. So 16 divided by 8.85 and then divided by pi gives 0.575, so 57.5. 57.5 newtons. The 2 protons fuse together. Yeah, maybe. Explain how the protons are able to remain together. Right, this has got all manner of misleading stuff in it. Right, what they're wanting to get at first of all is that they have got within the range of the attractive strong nuclear force. Now, but as we have mentioned before, two protons held together by the strong nuclear force is not a stable arrangement. It's the same with two neutrons as well. It's not just because they are electrostatically repelling each other. There was that whole, remember, with how protons and neutrons fill up energy levels inside the nucleus in a similar way to how electrons fill up energy levels around the nucleus. And you want to have particles that have got aligned spin in order to make them most stable. And this is then prohibited by the Pauli exclusion principle if you've got two identical particles, i.e. two protons or two neutrons. So this is not a stable arrangement. Say and explain how these protons are able to remain together is misleading. If you've got two protons together, you will get beta plus decay. One of those protons will decay to a neutron and you'll end up with deuterium. Positron will be kicked out along with an electron neutrino. So little bit misleading what they're saying there in part B. Right, moving on to part C though. Explain why the proton must have a very large velocity for the fusion to occur and the protons to remain together. Right, well, there is, we've got this electromagnetic repulsion between the two protons. So you need a high velocity to get them close enough, to get, close enough to for the strong nuclear force to take effect. So just turning that into a more coherent sentence. But yeah, not too bad apart from, I'm not happy at all with part B on that because it really is leading people up the golden path. Right, the third one, this will be the last one we look at in this little set. In the core of a nuclear reactor, one of the many fission reactions of the uranium-235 nucleus, so again, this is our induced fission, state one quantity that's conserved. Well, I only want one quantity. I mean, you can have everything: nucleon number, charge, lepton number, baryon number, energy, momentum. So let's go with, let's say nucleon number. You can have any of them. There's so many of them. I can't even write the word number. Right, there we go, nucleon number. Figure 4.1 illustrates this fission reaction, or it could do. Label all of the particles and extend the diagram to show how a chain reaction might develop. Right, so we've got this neutron here. Again, I haven't given enough space to write things inside, but let's put all of the neutron bits on, all these 1, 0 ends on those. So that's dealt with that on the way in and two of them on the way out. We now have to label. It doesn't really matter which way round we're going to put these down. So we'll do the xenon at the top and the strontium at the bottom. Not that it really matters, but that's these two here. And then we need to extend the diagram to show a chain reaction. Right, so chain reaction means that at least one of these neutrons that's the product is now coming round and being the neutron that's inducing further fission. So we need another uranium-235 92 over here. So it's going into that, and then we're getting the same thing happening again. So we want to repeat all of these arrows that we had on the original diagram. I mean, you could do this twice. You could do it for the bottom one as well, but let's not get carried away. We're just putting all this again, the same stuff that we had before. So that is still a chain reaction because we've got a chain going on. This is now linked to that one, and then we can link on to the next one. It's all down to the control rods as to how many of these reactions are going on. If we take the control rods out and there's nothing absorbing these neutrons, I mean, this one, you'll then have another one with uranium, which will go on to more products, in which case the reaction is accelerating. But in this case, we just got a 1-to-1. We'll assume that this one has gone off to the control rod and that neutron has been absorbed there. So yeah, there we go. So a quick batch there. I've got another batch of 3 in the next video coming up.